So hello everyone, this is lecture 77 for the mathematical physics. The last lecture we are discussing about the Laplace transform and we discussed the first shifting theorem. So today we'll discuss the second shifting theorem. So before that we need to understand what is unit step function because this is a complete theorem based on the unit step function. So unit step function is defined in this way, means it will be 1 if t greater than 0, it will be 0 for t less than 0. If we show graphically, then ut will be represented by this, it will be 1 for this and 0 for less than 0. Now if you need to plot this unit step function for a t minus a, how can you do that? Means this complete value will be greater than 1 when t is greater than a. So t is greater than a will give you 1 and t is less than a means this complete value will be less than 0. So it means it will give you 0. So t less than a will give you 0. Now same if you want to plot t minus a and t minus b. So t minus a, this will be a curve, and if a is greater than b, then a will be here, and if b is less than a, so it will be here for b. So how can you write ut minus a, ut minus b for a greater than b? Now see, ut minus a is starting from here and ut minus b is starting from here. So if you subtract, then first it will give you 0 minus 0 because this is 0 here, and this b is 1 here, and this ut minus a is 1. Sorry, this is 1 and this is 0 here. So ut minus a minus 1 means 0 minus 1 will give you minus. So that's why you will get only curve here, and again you have 1 and 1, ut minus a, ut minus b both are 1, that's why you will get 0 here. So you will get only in this region the graph. So this will be like this for a greater than b. Now if you need to find the ut minus b minus ut minus a, so that means here you will ut minus b will be 1 and a will be 0, so it will give you 1 here. So here it will be positive curve, again it will be 0 here, so you will get only curve here. So this will be ut minus b minus ut minus a for a greater than b. Now if you have something function like this 5 sin t ut minus 2, so first let's plot for the 5 sin t. So amplitude is 5 and sin t curve we already know, this will be like this, and this is pi 2 pi. Now let's say 2 is something like here, then this function is defined only for the greater than 2. So greater than 2 it will be as it is because it will be 1, and less than 2 it will be 0. So this curve will not be there, so this will be your resultant curve for this function. Same we see for the 5 sin t minus 2 ut minus 2. So see, this sine function will shift to toward the right by 2, means at t equal to 2 you will get 0. So means this 0 will be at this point. So this curve will start from here like this, and t equal to 0 you will get something like minus sine 2, so it will be somewhere here. So this will be a curve. Now again the curve less than t means t is less than 2, that will be 0. So you will this won't be there for this function, only the curve will start from here. So this will be your resultant curve for this function. This is pi plus 2, 2 pi plus 2, this is pi plus 2, 2 pi plus 2 and 2. So that's how you will define this curve. So I hope you now understand how we can represent the unit step function and different functions related with this. So let's move to the topic, that is t shifting. This is the second shifting theorem, is called a t shifting. Why? Because here we have the shift in the t, and the first shifting theorem is called the s shifting because there we have the shift in the s. So if lft is defined as fs, means for Laplace transform of ft is fs, capital Fs, then Laplace transform of t minus a ut minus a will be equal to exponential minus as fs. So this is a simple formula you must remember. Whatever a is here you will put a here, and it will be simply Laplace transform of ft will give you fs. So let's take some example. If it is exponential minus as, means this for the inverse Laplace transform of the exponential as fs will give you this again, ft minus a ut minus a. So you must remember this also. So let's take an example. It is, before that, what will be the Laplace transform of a unity step function ut minus a? So let's find it. Ut minus a exponential minus st dt. So see, this will be 1 for t greater than a, so and 0 for the less than a. So it will be defined for a to infinity only, for because less than a it will be 0. So a to infinity will give you exponential minus st dt, and it will be 1. Then it will be, means just integrate this and put the limits, will give you 0, and minus a will give you this. So this will be your answer. Means Laplace transform of unit step function is exponential minus as divided by s. So these are the standard results you must remember. Now let's see some examples. You need to find the Laplace transform of t minus 1 ut minus 1. So this is the form. Means wherever you will have this unit step function, you must apply this t shifting or the second shifting theorem. So it is a, in place of a we have 1, so it will be exponential minus as. A is 1 here, divided by the Laplace transform of ft is, means here it is only t, so it is t for 1 upon s square. So that was the formula. Fs was Laplace transform of ft. So this is 1 upon s square. Now for t square ut minus 1, now you must write this in this form first, that t minus, it should be function of t minus 1. So how can we write this? T minus 1 plus 1, we can write this way, ut minus 1. Now open this square, it will give you t minus 1 square plus 1 square plus 2t minus 1. So just separate these terms. First t minus 1 square with the ut minus 1, then only 1 square will give you l ut minus 1, and then 2t minus 1 will ut minus 1. So we just separated these terms. So here now you have this function in terms of the t minus 1, and this is square of this. So this is again, means you have the 1 here, so e to the minus as, a is 1 here, and now you need to find the Laplace transform of t square. So t square will give you 2 by s cube plus Laplace transform of unit step function exponential minus s by s from here. Now for this, 2 is constant, take it out, and it will be a minus s. My a is 1 here, and it is for the t, Laplace transform is 1 upon s square, so that's why you will get this result. Let's take this Laplace transform of cos t ut minus pi. Now how can you write this? First you need to write this function in terms of t minus pi. So how can you do that? So you know cos pi minus t will give you minus cos t, and that will give you again cos t. So that's why we take a minus outside in this. Now you can write this as t minus pi, that will remain same, because cos minus pi is minus means cos pi. So minus cos t minus pi ut minus pi. Now this is the form of the second shifting theorem. So we can directly write, in place of a we have pi here this time, so it is minus exponential minus as, and the Laplace transform of cos t as s upon s square plus 1. So we already know this result, so we can directly write this. Now we have ft equal to et, and it is defined that t is only, this is defined only for t greater than 0 and less than 1. So when the function is given some limit, so always apply the unit step function. As we remember here, to define the function from a to b or b to a, we did this ut minus a minus ut minus c for a greater than b. So this function was only limited into the a and b, so that's why we need to apply the same condition here to limit this function between 0 and 1. So it will be ut minus ut minus 1. So it is ut minus 0 and ut minus 1. So now et is limited between 0 and 1, otherwise it will be 0. So that's why we can write ft in this form. Now if it is in the unit step function form, we can easily find the Laplace transform. How? Using the second shifting theorem. So et ut minus et minus 1, we can write this in this form, because we need to write this function in the form of t minus 1. So now this is here a is, means here a is 0, so you will write ft e0 e minus as will give you 1, and Laplace transform of ft, that is et, will give you 1 upon s minus 1 minus e. Now this will give you, here a is 1 here, so it will be e minus as. So divided by the Laplace transform of et will give you 1 upon s minus 1. So this will be your Laplace transform. Now we have this function ft equal to tan cos pi t, where t is limited between 1 and 2. So we need to apply the unit step function ut minus 1 ut minus 2 with this. Now this function is defined in this way. Now just multiply this, and now we have to write this in the form of t minus 1 and this in the form of t minus 2. So how can we do that? So just write t minus 1 here, because it will give you pi t minus pi, so pi minus pi t will give you again minus pi t, so it will be plus. So that's why you can write this in this way. And here also pi t minus 2 pi, so 2 pi minus pi t will give you pi t again, so that's why it will remain minus, because here it is 2 pi. So we can write this form in this form, and now this is in the form of t minus 1, this is function of t minus 2. So we can use the second shifting theorem. We'll just apply a minus, here a is 1, so a minus as, and the for Laplace transform of cos pi t is s upon s square plus pi square. Same here a is 2, and cos pi t Laplace transform will be s upon s square plus pi square. Let's see the inverse example. So L inverse means Laplace transform will be s of s over s square plus pi square exponential minus 2s. So this is in the form fs exponential minus as. So we know here, now we compare, a will be 2, and ft is cos pi t, because this is the Laplace transform of cos pi t. So we have ft and a, so now we can write in directly cos pi, means this is the formula ft minus a ut minus a. So ft is this, so it will be cos pi t minus a, and ut minus a is 2, so ut minus 2. Now this is 2 pi minus pi t, it will give you pi t again, ut minus 2. So this Laplace transform will be this. So you must remember these formulas. Now let's see how can we use the second shifting theorem for the differential equations to solve them. The equation is given y double dash plus 9y equal to 8 sin t and 0. And it is for if t is greater than 0 less than pi, and this is 0 for t greater than pi. And initial conditions are given y0 equal to 0, y dash 0 equal to 4. So first we need to, if this is given in some range, we need to write it in the form of the unit step function. So how can we do that? So it will be 8 sin t for ut and ut minus pi, just put the limits inside it, t minus 0, t minus pi, and this will be 0, so you don't need this, it will be as it is, because for t greater than pi this will be 1, this will be 1, so this will become 0 automatically. That's why this complete thing can be written in this way. Now take the Laplace transform. First multiply this 8 sin t ut plus 8 sin t minus pi ut minus pi. You can write this because this will again become minus pi minus t will give you minus sin t, so it will give you minus 8 sin t. So you can write this 8 sin t this in this way. So we did this only to get this sin t in the function of t minus pi. So just take the Laplace transform of this equation. We already know the formula. Y double dash will give you s square y minus s, and this y0 is 0, and y dash 0 is 4, so this will be here, plus Laplace transform of this will give you 9, y will give you capital Y equal to, now Laplace transform of this. So again use the second shifting theorem. It will give you 8 upon s square plus 1 plus 8. It will give you exponential minus pi s, because here a is pi, it divided by s square plus 1, because that is for the sin t. Now take this y common, it will give you s square plus 9, and the minus 4, this is 0, equal to this. Now from here this minus 4 will be in the right side, then take the s square plus 9 in the denominator of all of them. It will give you y equal to 8 upon s square plus 1 square plus 9 plus 4 over s square plus 9. 8 exponential minus pi is divided by s square plus 1 s square plus 9. So this is equal to y. Now you need to find the yt. For that you need to take the inverse Laplace transform of this. So let's see how can we do that. First we need to separate all these terms in the form so that we can easily take the Laplace transform. So y is can be written as 4 upon s square plus 9, and this complete can be written in this way. You solve this, you will again get add 8 upon s square plus s square plus 9 plus exponential minus pi s. This can be written as 1 upon s square plus 1 minus 1 upon s square plus 9. So this was, we write it in this way. Now multiply this with and this with this. So for this, take 4 outside, it is something for 1 upon s square plus 3 square. So that will give you 1 upon 3 sin 3t, the Laplace transform, inverse transform. And this is 1 upon s square plus a square, a is 1 here, so it will give you sin t. Here it is 1 upon s square plus 3 square, it will give you 1 upon 3 sin 3t. And now use a second shifting theorem to take the inverse. It is e minus as fs, so that will give you ut minus pi and sin t minus pi. And for this it is 1 upon s square plus 3 square, so it will give you 1 upon 3 sin 3t minus pi. So I do use simply this formula, this one, and we get this result. Now let's solve this little bit more. This will give you pi minus t will give you minus sin t, and this will give you 3 pi minus will give you again minus, so it will give you plus 1 upon 3 sin 3t. Now we have our solution. Now let's write it in the form of range again, because we have the question in the range. So how can we do that? For the t greater than 0 and less than pi, this will be 0, so we will remain only with these three terms. So this will give you 4 upon 3 minus 1 upon 3 will give you 3 upon 3 1, so it will be sin 3t plus sin t. So this is for this range. For t greater than pi, this will be 1, so this will cancel out, and 1 upon 3 sin 3t will cancel out this, so we will get only this 4 upon 3 sin 3t. So this will be your solution. Now let's see what is the Laplace transform of Dirac delta function. For Dirac delta t minus a, it is Dirac t minus a exponential minus st dt. Now this will be defined for only t equal to a, so just this will be 1 for t equal to a. Put a here, it will be e minus as, and this integral will give you 1. So this is your Laplace transform for the Dirac delta function. Must remember this result. Let's see a question based on this. So we have a differential equation y double dash plus 3y dash plus 2y equal to Dirac t minus 1. So we need to solve this. So again apply the formula for the differential we used. For y double dash s square y minus, now these initial conditions were given that f0 is 0 and f dash 0 is 0. So we just put 0 0 here. So this will give you s square y, and this s multiplied 0 minus 0 Now for 3y dash, it will be 3sy minus again f0 is 0, so that's why 0 plus 2, and y will give you capital Y equal to exponential. Now the Laplace transform of this is exponential minus as, a is 1 here, so it is exponential minus s. Now see from here, this will be 0, so take the y common. It will give you s square plus 3s plus 2. So ys will be exponential minus s divided by this. Now you can separate them, s plus 2, s plus 1. And again we can write 1 upon s plus 2 and s plus 1 as 1 upon s plus 1 minus 1 upon s plus 2. You can use the partial fraction here. Now to take the to calculate the yt, you just need to take the inverse Laplace transform. So it is exponential minus as fs form. So just take the Laplace transform, it will give you ft minus 1 ut minus 1. So it will give you this. It's like you can see that this is exponential minus a is 1 here and s, and this is complete capital Fs. So inverse of this is exponential minus t minus exponential minus 2t, and we need to put the t minus 1 here, ft minus, this is the solution using the inverse. So ft a is 1, so t minus 1 ut minus 1. So just substitute here, so it will be 0 for 0 to 1, because this will become 0 for 0 to 1, and for t greater than 1, this will be exponential t minus 1, means use this function we get. So it is t minus 1 and t minus 1 here, so it will be this. So that is your solution. Now there is some differential equations, means you must remember these results. These are very useful to calculate the Laplace transform of this form. Means you have any t and ft form, and you know the Laplace transform of ft, that is fs, then any power of t can be written directly as the differentiation of fs. Means for t equal to 1, it is minus f dash s, and for t square ft, Laplace transform will be minus 1 to the power square f double dash s. So the power will be equal to the order of the t. So for t n order, it will be minus 1 to the power n f and s, means nth order derivative of this will give you Laplace transform of t and ft. So let's take an example. It is t sine beta t, so it is 1 power, so it will be, we will use this, so it minus dy ds, and we know sine beta t, the Laplace transform of sine beta t is beta over s square plus beta square. So the differentiation will give us this. So this is the result, we already seen this result, this is the same. So that's how we can calculate easily the direct these things. For t cos beta t, you will get dy ds same, this will give you s square minus beta square divided by s square plus beta square whole square. So you must remember this result. So that's all for today, thank you everyone.